hour. I think I missed out on recording the first hour session. That's fine. But feel free to ask. If not, I think we'll take a bio break for 5 to 10 minutes. Panel remains open. I'll be off for 5 minutes. The session remains on, but we'll connect after 5 to 10 minutes. However, last explore the different options that I have told you. Pick again. One of them is if had a bit of overlap or interference and no penetration contact. It is any such case is not case to be simulated. So you understand this is more of a modeling mistake than anything else. There are cases where there is example that of shrink fit, etc. Then simulate shrink fit by using the or here. It is selected under that option, and after we'll calculate to get them back to the original shape, and then it will go ahead. If not, actually we need to overcome the interferences between parts before you do any analysis in sim. Anyone else has any other questions on the contact discussion that we had in the last half an hour? There is a set for the shrink fit. Is it and must be overlapping each other? Answer yes. Rather go into this example. That is better. Let me check where it is. Okay. Now regular example. This one I'm about to use for shrink fit or the shrink fit simulation. If this image over here, there is a kind of handling interference that is present, and the thing that is going to help the software to set shrink fit. Apart creating the modeling interference, what we need to do is let me get view back to proper. Yeah, there are also explode it. Okay, so the way shrink fit is created is just selecting those two surfaces which we are interacting, and the kind of contact will be shrink fit. That's it. So what we see is or whatever interference was that will revert back, and we think scale. Let me make it at a true scale. Okay, this is so after it is going to come back to a kind of consolidated stage. There is no penetration between each other. If you might be able to see it. Not much visual. That's okay for that. This is what it is. Okay. Whenever there is one more question which is asking, where is a global bonded contact? Now this is as I whenever we create a new study, this comes by default. Okay, not that a user has defined. Local contact that is being created is going to overrule that particular global contact. So this contact has no job to do here. It is wasting the calculation time. So mergation, if at all such cases are there, the software is creating it, asking users to just dig it as a study and define all the local contacts. So global contact and define the local contacts, that would actually be more accurate. There is, can you please explain the difference between contact and the contact set? I think discuss this in the last few minutes. I'll read it, then put it very simply. Um, Local or contact set is between surfaces or edges, and contact is typically between parts or bodies. That's it. Next, it's proportional to the amount of interference. Yes, that is true. It is directly related. And you have on the top contact. Any option is, what is contact pressure? Um, Now you understand that we have these two things. Number one, no penetration contact, and second is the shrink fit contact that is present here. So when now in this case, when there is a shrink fit contact, when the part is consolidating, that is the inner part is compressing, outer part is expanding, huge amount of forces will come into picture at this particular junction. And those are represented, and those are the ones, um, those are the ones which are really represented by this contact pressure. So whenever we plot this contact pressure, it is going to show us the forces that might be present between those two surfaces. Otherwise, if it is a no penetration contact, it and you are using this plot, that will also tell you when part comes and interacts with other part, what kind of forces that it is going to exert on the other part. Can you please repeat on global bonded contact? Number or why is used? The contact has no significance in the analysis. You can simply delete it and you will get the same result. Present just for the because of the fact that whenever you create a new study, the default condition or the default thing that options that it is one of those default options. They don't want to edit it. We can okay. So the other way around, the local contact, that is the shrink fit that we have created, is overruling the global bonded contact, and that is the one that is going to work here. So if you remember, we discussed on the hierarchy of contact. So the fit is the one that is going to overrule contact. So contact, and that is going to global contact will not have any significance. Can simulation calculate the shrink fit force required? Now, what you are saying, you might be wanting to say that if one part, that is a shaft, that is being pushed into a bearing or something, you have to find out how much force is required to push this particular part into the other part. Now, one aspect is this one, the contact pressure, that will definitely give an idea on how much force is required. The other part could be, now if you see the contact pressure plot, it is of a pressure plot, and maximum pressure that we are seeing is around 134 megapascals. Therefore, we can multiply this by area, and we can know an edge force that might be required to that might be coming into this junction. The kind of analysis could be, it is not over here, but we do a non-linear or dynamic analysis, and we push the shaft into the bearing and see how much reaction force is required to push that particular shaft. That will tell you how much force is required to this shrink fit. Okay, question which is, what is the difference between yellow color and orange color arrows? Is actually, if you see the plot over here, this plot being represented. That's it, nothing much. Yeah. So this is just like any other contour plot. Uh, that just for whatever reason, actually the maximum area is by the yellow color, which is around 100 megapascals. There are two parts here and there which are at lower color. Say for example, this red over here. There it is, or calculation errors which are present locally. Another question. Frankly, I actually covered one more topic or lesson also which I wanted to discuss today around shrink fit. Okay, one more other aspect of this lesson is the symmetry condition. Let me go back to a better view. Let me have, okay, the part with my standard view. Uh, if you observe it over here, okay, a bit of discussion in this topic. Now, this is shrink fit, so you can understand one part is present inside another, and we are not holding this part anywhere. We are not holding this part anywhere, any of this particular complete geometry. So it is the case that we, because you, as we discussed yesterday, huge calculations happen and can be forces as small as microns in any directions, and that can lead to this part flying off. Okay, so kind of instability that can come and it will not fall. This, we try to take a few vertices which kind of away from the place where we are going to apply forces or loads, and those vertices can be used for resting the body and avoiding from flying off. Now, in this, we know that some certain way in radial direction and circumferential direction there could be resistance. Circumferential because of symmetry condition, and this because of shrink fit. However, in the axial direction, that is in the y direction, there is no restraint and the part can fly off. In such cases, we can use the restraint and just to stabilize the model. So this is one way of doing it. On the other hand, it could also be that we can use, as a few people were asking, soft. So use these soft things to stabilize such small forces. So there are any such small forces which are leading to instability in the model, then we use it and that will stabilize it. Yes, pretty much that's it. Second of discussion is towards this particular boundary condition. Hmm? In one way, if you see this object, um, I would say this is eligible for both symmetry and what is circular symmetry. So if we are taking 1/4 geometry, so we can use this symmetry option and can define distances which are going to act as symmetry. So the software is assuming that other part of the geometry is also present. It I suggest that is going in that direction. However, I would suggest we can also use creates the geometry and can go in for circular symmetry. So each option can be used in this case wherein we select the surfaces and select steps approaches to show you you compare these stresses, six triangles here. If I compare it with the other one, the cement should be almost the same. Yeah, 3 megapascal. So this like to highlight. There could be cases wherein symmetry cannot be used, only axis symmetry can be used to give appropriately and use it. Time for me, I would say we have finished with the discussion on symmetric and symmetric boundary conditions. If no, move on. Mm, so example, solve it. Apart from that, there is one more uh, exercise also. Even that is interesting, where you are going to two kind of rings that are coming into contact. That would be interesting. Let's have a quick discussion on this question. I open the chat window. I would like to get the inputs. Yes. And the available component condition types are three different kind of contact conditions. Which can you highlight? Okay, one day. Allow penetration is the second one. Bonded addition, fine. Far away, I'm getting the right answer. Can I go second question? The dash no penetration condition applies to the interfaces only. Dash contact feature gaps and initial separation. Yes, this is a point. Frankly, even I missed out when I discussed this. Were thought. Okay, one of them has given the right answer. Uh, that is dominant no penetration condition applies to initial touching spaces only. So if there is any initial contact, then it makes sense. While local contact may feature gap and initial separation. So if there is some separation and there is scope or connection between those two, it will take into account those things. So that is a difference between component and local contact. The last to see in this lesson, the light was suppressed and a fixed geometric fixture was applied on the. So you remember we apply fixed geometry condition on the face or the place where it is going to hold the component. So this assumption was not made. What else could we do? One is saying that ignore it. How can you ignore it? If it there will be any resistance to balance the system. We said one particular option is not being discussed. We'll skip it. In that, there is one which might be useful here. And answers, but not the answer. Any thoughts? How about using a virtual wall? Use virtual wall. We can create this particular wall exactly. Um, is closed. We can virtual wall exactly at the location where uh, vector here. So we can create a wall here and give the stiffness of that particular wall. So that this is one of the ways of doing it. The second thing could be we actually create a part over here, and then that is going to be representing whatever component is being held. So you can do that also. So two options that you can use. Option I believe we discussed it. On that, okay, just show you this option in terms of way we can see the spaces. Now, one of the basic spaces that we saw was 1 by 6 stress. Sorry, I think you missed out on the answer. Answer to the last question is using virtual wall. Did you get it? Okay, one. Yeah, one of you asking what is the answer to question 3. The answer to this particular question is virtual wall. Back, by default, the 1 by stress, as it is a derived quantity from the principal and shear stresses and the north stresses that you use. But again, it is a resultant quantity of ux, uy, and uz. So it is a resultant quantity. Strain should again, this is the resultant quantity. But all these things, now what is root stress? This is naming that has been given. But ultimately, it is the stress in the one normal direction. In some cases, we have the option of specifying an axis source here. Or the direction in which we want to see the stress, we can specify it over here and select F direction. It could be Sx, Xy, Z, etc. So that, and one of the ways, like if I show you how to create a plot, I can take an example of a displacement plot. I like to select radial displacement. For that, I can select X direct some axis as the reference to plot it. I can do this so that I can see it, and this is the way it is. Let me go in for the truth scale. So this looks. So if I select and do that and play it, it might look like this. The ADL displacement that is happening in the part, you can see the blue thing is actually the part is compressing. The red one is it is expanding and in out. So this is an exaggerated scale, and you can see how it works. So basically what I'm trying to show you, if you want to see any directional there's the option of selecting the reference and plot. Example on chain link mechanism, uh, it also discusses on what could be right boundary conditions to be used, discuss what could be the incorrect way and the correct way. It should be useful. And I think now we'll move into the next one, which is called as factors. Before questions, any further questions on this? What as of now? Not sure if you understood the answer to this question. To say is we need to use virtual wall and give the stiffness of the body. That could be one answer. Second answer is you actually model the body. Looking at uh, I'm opening the right model. As I told you, there is a bit of difference in terms of the model is available in training manual and the lesson summary. So I placed it. Okay. Yeah. As discussed as of now, one part was using the uh, using to define the connection between two parts. The second concept would be to use the connections. That's what we are going to discuss now. Talk about connections. We have many different types of connections. Start from rigid connection to rings and bearings, etc. So most practically available connections are available here. We need to understand what exactly they are. So typically, if particular example could be a bolt, we are not actually modeling the bolt, but only modeling the or the properties of the bolt and what an effect of the bolt at all it was present there. So bolt is a certain amount of initial pretension, it is stiffness. Are in the performance internally. But it is this is it. So have a look how they are created and what are the different options. Okay. This is there is a exploded state of this one. Yes, explode. It is easier to create those connections. So there is a pin that will fit between this place and whether the pin is already present, but the interaction between these two can either defined by creating a contact set or using a pin. So we are creating a pin, the outer surface of the top and the arm and the internal surface. So this is created. Pin has different things. One of it would be whether there is a retaining ring. So this is going to decide if there is going to be any axial movement of this ring, whether any whether you want or you want to restrict any rotational movement. Again, that can be decided here. Other advanced options in terms of say all there is it is free rotate. There will be some friction or a movement in the rotational direction could be restricted. That can here. Mm, NS can also be given. Further, we can define the material of that pin. So either from this material database or we can actually define the values over here. We can do that. Finally, strength pin I can come from the material property thing or we define it. Now, interesting part is these are not used for calculation, but as I told you before, the software is going to calculate the stresses that are coming into all these components. Either those will be used for those be used for further calculating the kind of safety for those localized things. So calculations are done, and we know the axial forces in those um, in at the localized condition. So we compare the forces that are coming from the design to the strengths that have been given here. It is going to tell us whether it is okay or there needs to be a change um, at condition. So this is what it is, and we can do it. We can talk directly. Yeah. Which after a safety factor, again it is more of a post processing thing. The settings we have three pins that have been defined here. Next spring, the ring that is going to add some stiffness to bring the wire back to its original location. So you see here we have different springs, aggregation spring, spring, or extension only spring. First compression and extension spring. These can be created between flat faces, cylindrical faces, or locations that you want to specifically select. So vertex option or the location option is selected, and we're selecting one point on one part, and on the similar side, one more point somewhere over here. On the second for springs, we can specify the axial stiffness, tangential stiffness, and rotational stiffness if it all has. And from that, it can also have certain amount of pre-tension or preload, pre-force that is also present, and that can also be defined over here. Um, but might be of interest. Thing we discussed. Third one is bolts. I see we have multiple different bolts. By the way, another 2014 new feature. As if um, created using Wizard bolt wizard, first Explorer option to create the default bolt. When we create a new study, we have an option to export the related settings as it is. In the past, we were required to suppress those bolts or get rid of those bolts and then create the definition for the different bolts in a separate way. That was the approach in the past. However, now we can create them directly. Uh, so you can see here we have these different options bolts. You can select whichever bolt is going to act. Surfaces have to be selected. we have the option of tight fit, which will, if at all there is a gap and threading happens inside at a certain location, we can select it and select the appropriate pieces, or we can say tight fit and say that the threading is present all over. Multi remains as we discussed before. Also has the option of giving the torque and axial forces installed directly. A series of bolts and you are doing symmetric analysis, then you can use this option symmetry. So those are the options or options for bolts and bearings. The only difference could be and alignment stabilization, and we can specify rigid and the flexibility of the bearing in lateral axial direction. Spotwise is a very good exercise example in the exercises. If you this particular part over here, welds are created somewhere all around over here. So we need is two sheet metal or surface geometry. The reference geometry by defining points along the length, and we need to just select those locations to define the. If you see the definition over here, we are selecting two faces. There is the two components that will be welded. Like the location where they will be welded, that will be selected using the point option. Finally edge weld. Yeah, this is another new thing. The examples could be connections between surface bodies and solid bodies. At the moment, at least one surface body is required. Connections wherein edge weld is present. We can select things. We can find the electrode that has been used for welding over here as per two different standards. And on that, by the way, we can also select the kind of weld. It is a single-sided, double-sided, or a groove thing. And on doing analysis, again, we can understand the edge-related details in the sense of whether the given thickness is enough, would be the required thickness across the length. All those details can be understood. I think that is links and connections. These are more towards um, applying relative motion between two parts. So it has a bonded contact as well, but do not have any rotational degree of freedom. We are saying that one particular reference point on one part is carry any other reference point, and no kind of relative motion between these 2 points. So this could be one thing, and the other could be the rigid links, wherein here, but see we have a broader aspect of we can select faces to give the rigid connections. So if there are any two faces between you do not want any relative motion to happen, then with this option. Other way around, whatever motion is happening on the other face is expected to be happening on the face also. Then the reconnection option comes into picture. This is what we have to understand in connectors. A combination of contacts and connectors we can find assays in detail and simulate it to the minimum accurate conditions. These two topics that we discussed this morning should help you do that. I think time for questions. I'll open it for questions. if uh, if I want to involve frictional forces, resistance, and surfaces of pin and component, I need to check the with key and enter the friction value. Is it? Let me check. We're going here. Um, there's no such thing called friction in between itself. So we are not specifying the frictional friction resistance, but we have the option of specifying this necessity. So if you know the forces that are coming due to frictional condition because of whichever way they are connected, then yes, can do that. However, if you expect no relative motion to be happening between the pin and the part around it, then you just select um, for these two options of pins that are with key no rotation. So there is a key which is restricting the rotational motion, and second is with retaining ring, no axial movement of the pin. So he is asking me, can you explain me in more detail on what pin formation? Can you tell me what exactly are you looking for? Second part of the question, I think I can answer, wherein you are asking how do we optimize edge welding by using edge weld connector. So, tell you what happens, which location you edge weld edge welding is done, you create them and solve the analysis. After the analysis is done, you can see the forces that are coming in the edge weld, and you can understand how the forces are varying. So it could be wherein we are understanding the, say, if weld is along a particular axis, we can know the thickness variation across that particular axis, and we first understand thicknesses that I have given, are they required, are optimal, or do I need to change them to improve it? So that is the kind of optimization that you can do once you get the result edge weld connector. One of we want to know bolt series mark in options. Let me check it. Okay, just a moment. Bolt. If I go to bolt option, we'll get this option now. Bolt series. Okay. Now only number one. It could case wherein huge number of um, um ceramic or um, okay, series of bolts are there, and number one, you might be using only half of the, because of symmetric condition, you simulated only half geometry. So in that you can use this option and tell which is those surfaces which are going to be half. If we here, we also have the option of 1/4 symmetry also, so we can use that as well. Uh, that can us in simulating multiple number of bolts. I think then they help, if I remember correctly. Let me check the bolt part of it. Bolt. Oh. In the image, there is a good image in the help or in the training. Yeah, here it is. This is what I was looking for. So Okay, if you store here, that should tell you. So if you add to this image, if there are multiple components, with bolts, the bolt series will be useful. Around these are present as well as some symmetric condition is present. Then actually the condition will also be useful. I hope. Second one is what pin stress area. I think it is as simple as the cross sectional area of the pin. Then option, but pin and yeah, I think this one. Yeah, cross sectional area. That's it. Nothing much. The area for calculation of stresses. Go to pins in the mail when this opens. Yes, I are square cross section area. Frankly, we are done with the two big options, pins and connectors, and we did a bit of discussion on the initial part, that is the stresses and those details. If you review, almost 2 hours now. Before going to the last session, I will take 5 minutes break, and I will start after 5 minutes. The different options we have discussed, questions on those topics. You can keep on asking questions using the chat window. If not, take a 5 minute break. We'll call and after 5 minutes. questions on the topics that we have discussed as of now? Any questions? So I'll move on. Um, Fine. So next important topic, which is called as incompatible mesh. If you here, that itself will explain you the difference between these two characteristics. Further, for your significance of more into bonded elements and especially if there is bonded contact. Now, this one, the image below, example of a uh, direct contact with compatible option. And this big image is that of this bottom part, wherein you can see in one or the other, there is an exact imprint of the top plate that is present here. So it is imprinted on the bottom cylindrical part. It is such that it is a coincident node, but actually there will be a single node that will be shared between these two parts. Now these two are different bodies or parts connected using bonded contact. It's not a single body, whereas simulation it will be connected using bonded contact and connection is complete. Compatible option is used where the does that a single node it just comes into picture and shares the connection between these two. Such cases, you can say it is if it is a single part from top to bottom. They are not two separate parts. And other round of saying it could be a scenario wherein you have bodies, you have merged it, and you are then meshing it. So that's the scenario over here. However, cases wherein this small body or the top, say, highlight it over here, this particular plate is very small, and the bottom plate is very huge. The bottom link is very huge. In such cases, uh, um, you see meshing failure. The mesh may not be created because it is not able to achieve the continuity that we are expecting in a compatible mesh. In cases, it can make a better job. Observe this geometry. Both these parts are made separately. Something called as constraint equations are written to two parts at the localized condition. And so this is the biggest difference. And generally something like this. And this is more explanation on this topic. If you do the properties of this study, you find something called as more over option. Frankly, even though it has been included in the training manual, uh, I for understanding, I would suggest not to worry too much about it. You can leave it at the automatic stage and the software decides it. But particular option is selected. Then if you see the image below, the around I would put it. In the past, the connection in such case would happen only between the localized nodes. So whenever the equation was written, uh, set body had certain number of nodes. Okay, body had certain number of nodes. It would be most adjacent node or elemental node on the body, and it used to connect over there. However, now with the more accurate bonding connection, it will ensure that all the nodes and elements of the smaller body connected to the big body appropriately. Definitely, that's a big difference, and it can it, not to discuss on this topic. Uh, if I go to the software, the option is somewhere here, and incompatible. And if it is non-touching faces, what are the gaps that you want to allow over there? So those options are there. If I show you the mesh, not created, let me recreate it. Date refinement is done, and continuity is achieved. It is incompatible, and mesh is not achieved. The connection is done because we selected bonded connection here. Then is done using equation. So, okay, any questions on this topic of company incompatible mesh? Multi-bodies. It is asking me how does solid simulation treat multi-bodies? Right in saying that it is just like an assembly. For simulation, um, it could be parts or multiple bodies. These are just different entities. That's it. The question which says, experience a problem of solid mesh in normal cell element can make compatible mesh. I did not have this question. What way does it affect the analysis? Typically, compatible mesh is, you can see, far more continuous and accurate. Then in incompatible, when we are writing equations, you have to change the stiffness of the body. So there is small change in stiffness. Obviously, the incompatible mesh geometries are far more strong, I would say, comparatively to the compatible mesh bodies, and that would be the difference. But around in a case when it is of a necessity, compatible mesh is a necessity at certain locations, and incompatible mesh again in cases wherein mesh is failing. Okay, around for all models, try to get a compatible mesh. If not, then move on to incompatible mesh. Yeah, asking for an example of an incompatible mesh. This one you can see here. This model is with a compatible mesh, and the way it looks. Any items on the topics that we covered as of now, or the incompatible mesh option? Which one is accurate, etc. As it is more of a necessity. Certain models cannot be messed with compatible mesh, might be required to move to incompatible mesh. Definitely, compatible mesh is far more accurate than incompatible mesh, no doubt on that. Okay, see any further flow of questions? I think close this. Let me go here. Okay. Uh, Lesson is going to cover almost similar things, but in terms of connection, but a few new things could be remote loads that we'll see, and in remote load would be a completely new option. Um, in the previous example, we used only pins and springs. In this example, we will end up using more options like bolts and other connectors. So float option, I think we discussed this yesterday. So it is a way of representing a remote body which is present, a body which is present, which is not simulated in the software, is actually present over there. So you can use this option to do that. And it's different options. One of them is load direct transfer, rigid connections and rigid connections, but using displacement option. So those are the ones. Let me see if I have a better image or explanation for these three. Both believe we discussed the options, but we'll see how they are created in the software also. Used again, this option which I said can be used for players, send them, and that's the way it can be refined. Let me model. Mm, okay. So here, um, good thing has been done here. If here, the bin actually created in the SolidWorks model, they cannot be used in simulation because we are recreating them. However, that in 2014 we have an option by which we can actually use those bolts. Let me check if it permits here. Oh, yeah. So create a new study. At the bottom, you can see convert tool fasteners to bolt connectors. Just select X. Automatically, all SolidWorks bolts you can see here will be converted to connectors. You can see automatically. Now, the blue color bolt that you are seeing more for visualization. There is such bolt present there. It is just a connector and it is for give connections. Now go to the settings of those things. This is all happened automatically. Be aware when this training manual was written or before that, this option was not present and we used to do it manually. I have to do it manually also. So all mentions have been taken, appropriate bolt connector is selected, the things, all the details come into picture here. Now this study that is present over here. Okay, here in sections, okay, these manually defined, they look a bit different, but this is the way it is. You select as asked over here, conical face where it is going to be fixed. You need to set the appropriate kind of bolt and the edge on the other end, the head, diameter, length again, and axial. Axial would be the options that we are selecting and creating these four bolts here to connect these two parts. Sets. So we are defining as we are defining a virtual wall. Let me check if virtual wall is already defined. Yeah, it is. The wall that has been defined. You can a place created to define the virtual wall, and that is be connected to the bottom surface of the um, uh, there. So one plane is there, second plate is there. That's it. Virtual wall is assumed to be a rigid virtual wall. Frank, the reason why this has been connected here is more to connect it to the uh, ground. Again, if you go to fixtures, we have something called as again bolt fixtures over there. If you had observed it yesterday, been used something called as foundation bolt. Those have been used to the connect the or the place where getting connected to the plane over here. So what we are defining, you can see here the plane, the virtual wall plane, and the one is the edge, the top edge of the plate. That's it. So rest of the things remain the same. To understand that this is one of the restraints over here, the common virtual wall and foundation bolts. Second, I have a huge set of no penetration contacts all over the body. Um, scroll down a few things. No penetration have been created at multiple locations. Tube is getting connected, etc. Almost basically. Okay. So these were the two, I would say, things. The new thing was or is in this body is the remote load. Now this actually the here. However, it is there is actually huge geometry that is present on this setup, and the force is applied on that huge geometry. So the force transferred all the way from that geometry to this bolt, and that being simulated using the direct transfer option here. So the cases where force will be applied, which is a reference coordinate system which can use to give the C or the center of gravity location of the huge body, and this is location that we are specifying here. The forces either can be enforced or we can also specify movement. And if I go, yeah, this is just for visualization. That's it. So and okay, let me check if I have more explanation on the transfer and the options. Need the image to explain it. If I get it, it would be easier. It's not here. This is not looking for. I get an image. I'll try to explain it in more detail. But the words over here make it pretty simple and understanding. So options that are used over here are to be read over here. I would say is a bit flexible in the first thing, that is the load transfer. However, it is one-to-one transfer. No movement is transferred over here. In the second, movement will be transferred. Okay, this is the called setup, but really this would be the setup with a remote load option. Now, in this case, what we are doing is we are the code mesh. We are seeing the results, and we are improving the mesh to get more detailed, accurate results. So you can say it is pretty hazard and the steps are not continuous. So definitely there is scope for improvement in terms of math, and that's what we do. Okay. So what it is in terms of lesson, which is lesson 7, in the present online or compared to old methodology, this was done 5 actually in the past. It went over there. Okay. Any thoughts? Minimum number of solid elements in the through direction is draft quality or if dash is high quality. Do you have any other question? Okay, it says that for this study, how to calculate the remote load uh, uh, location. Okay, I need to explain it a bit if I open in slide. Okay, Hmm, I, let me something. Give me a moment. Let me try something. Let me check if this helps. Help. I'll take this. So, this is our body, which is being analyzed. And on there is a huge crane-like structure all over here. It's huge actually. And for us, the interest is on this area, which is going to be analyzed. Hmm. We are kind of simulating this top structure, but we are going to analyze it. So what happens is this top structure has easy somewhere here. It is easy here. So what will we just this particular structure? We use locate that we have over here and be connected using rigid links or what mechanisms that we have. Now the point of C is what needs to be calculated from this bigger geometry that can be used directly over here. We find the mass of the body and the CG. That's it. That is more than enough. That's it works. The answer for the question that was present on the screen, the minimum number of elements is at least 3 for draft quality. And let me check it if it is 5. But answer on how to find the um, kind of the, um, CG body. Let me choose panel. Okay. Okay, then I think there is a bit of misunderstanding. The number of solid elements in through the next direction is dash if draft quality. So when it is draft quality, we have a mid-side node. So definitely we need more number of elements. When high quality, we already have a mid-side node, and we work with um, high quality lesser number of elements. So answer is 3 for draft and 5 for high quality. It is it is seen as exactly other way around. Say if I can do something with one element in draft quality or two elements in draft quality, I might be able to achieve the same thing with a single element in quality. It is a thin structure and we want to mesh with mm, elements, then I suggest to have at least 3 quality elements. If not 6 um, draft data elements for accurate results. Moving on to the next chapter, but before any questions? Then I am taking up a new topic, which is more towards the creation of shell elements. Okay. Now this is a simple example. If you can see here, it is of a solid body actually. It also has a mid surface uh, surf, kind of shell or surface that has been already created here. It is present over there. We will see the different ways in which we can create. When I create a new study, you can see here, solid and shell bodies are present. This being a case for um, this surf body is there, but typically it may not be there, and you actually exclude the analysis or surface or whatever. So forget one. Now, this particular whatever surface that we are seeing on the screen here, that we are seeing, we can present it using service in multiple ways. One is when you right mouse button click here, you'll get this option defined by selected spaces. So that you can see bases all around. Let me yes, bases are selected. You can see that we can define the thickness of those surfaces. You can see whether it is a thin cell or thick cell. I'll discuss what exactly it means by that. Offset. Now in this case, you can see the surface is presented by the inner surface over here, and we have the option over here to define what does this surface locate. So I'll say it is bottom surface. So definition, this is how it might look actually, by which we can define the location of the surface that we are playing with. Can be further defined to rather the visualization is permitting us to tell us how surface is going to be stated internally or visualized internally. So now the mid surface, I want this. This is the option that I need to select. I don't know the thickness, I forgot, but I think it is somewhere around 2.5 or yeah. So this is what is required. This is how it looks perfect. Um, option could be around that I don't have this. So as I told you, the surface have been already created in the solid geometry. You can actually use it. The difference would be we need to specify the thicknesses over here. Over here we have the option of selecting the location of that particular surface, which I will not be showing in this particular example, but be more towards sheet metal part. So geometry, which is a sheet metal part, will be automatically treated as surfaces in section. You can use that option also. Goals that have been already created here. You can see the setups. The method that I mentioned you has been used. It is already defined over here. If the central surface is fixed in options and certain conditions are used. By the way, this is another point we will discuss a little bit later, but this is a half cylinder, so we are using 7 additions over there. and let me checking. It's fine. Finally, pressure in okay. In terms of surfaces and applying pressure, ensure that we are applying the pressure on surface that is being meshed or used for shell elements. Sometimes end up doing that mistake because the solid entities are also present around. We might end up doing that mistake. Means we are selecting the right solid. Finally, oops, this let me solve it. A bit of has been done here by using different kind of uh, using different kind of solid elements, shell elements, and the results are being compared. How would be the results with solid elements and shell elements? I can't too much into it. You can do it on your own. With the method, create element. So once it's with the plane, we can maximum stresses around 80 megapascals. Let me stresses with source this one around 80 megapascals, but you can results the way they look. Um, um, and it is of validity, no, not it is only 1 meter across the thickness, and finally this one is 10 megapascal. So scope for refinement over here. By the way, for shells, we also have the option of looking results at the top plane, bottom plane. We can find membrane and bending the stresses. So available here. This it is. Let me anything. Okay. Out of the shells, which is very important. Let me go here. Show mesh. Okay, here the mesh, the shell elements are shown with two different colors. One of them is orange and gray. Now, in this case, it is all okay, but might face cases wherein, let me, okay, your arrow which is telling the thing, right, and something called as, I mean, we flip direction, yeah, here it is, flip select, if it is right click, switch element, okay. You can see, uh, if now luckily this was a simple geometry, so it could match. You see the alignment over here, certain are in gray, certain orange, certain gray. But in desirable condition, and we want to ensure that all the surfaces are of the same color and are aligned properly. So requirement, then we want to ensure we select all those surfaces which are not aligned properly. Next thing, you can just right click on the mesh, flip them. On doing that, they'll flip and they look aligned properly. This is most important step that to ensure that happens in challenge. This year that first of all the stress results will be good or correct if they are be correct only if they are aligned properly. I think these are yes. Next and the most important thing that I would like to discuss is this one. When you create these cell elements, you see this option of thin and thick option, that is thin and thick shells. We need to understand what exactly it is. First of all, when do we need thin cells and do we need thick cells? The bottom line of uh, what ratio should tell you those things. That is, if this path thickness ratio is more than 20, then you need thin shells. Other way around, if it is somewhere between 10 to 20, then we need thick shells. So the first thing is the difference. Uh, Basically, in thick shells, uh, the way the things that you are seeing over there, basically we are not too much worried or we are neglecting shear stress in the body cross section. Whereas there is no much variation that is happening across the thickness of the element. Whereas the thick option, then yes, it is true and that is being done. So other way around, for all for any geometry we can uh, safely use thick elements and it should be okay, no issues. However, uh, um, if I ensure that we do not neglect comparatively thicker joints which are meshed with shell elements and we not use thick elements. So ensure that we do that. Now the thing is that there is complex option will see over there. Unfortunately, that is not part of this training, so I'm skipping it here. So if you or you are attending the nonlinear and dynamic training, that particular will be covered over there. So questions, I can see a few questions flowing in. It says that if I change all the gray color bottom and orange color to the top, is it reproduce the same result? My answer would be yes, it is going to produce the same result. But we understand in such a direction that uh, there not be any inconsistency. That is, certain places are at the top and certain at the bottom. That is not acceptable and permissible. Second, which I want to convey is try what exactly the color mean. It is not the color, but if you are seeing this thing, it's telling this what we call something called as shell normal. So when I check the surface over here, you see there is a arrow that is coming up. Okay. This is telling the normal direction of this shell. So in short, this is the bottom surface and the top surface is somewhere above that. So we are seeing the bottom, top and middle area surface stresses at its thickness. That is what we are understanding. And of course, the inconsistency is not acceptable. It is fine that we change all the gray into orange. No issue. You should get almost the same result because we see the results at the mid plane. I was asking in the image is shown here, what is span? So I would say it in this way. This way I believe it is understood. So in short, it would be the shortest length in the geometry. Thickness would be the shortest length in the geometry. Whereas I would say it would be the length in the geometry. It is as simple as that. So you can imagine it accordingly. What I discussed of stresses, as I told you, we are getting bending and ambient stresses as well. We see and is it bottom surface? This is a good function. Okay, the edge weld connector as well is here, and you can store it and connect 30 minutes. That's it. There are questions now and the chat window. Okay. Frankly, I'd like to conclude today's thing by going through these questions and questions in the chat window in the next 10 to 15 minutes. What I would be covering today. Mm, uh, so we have covered almost 8 lessons in further simulation training manual. Try through them. Any questions we can definitely discuss today or tomorrow. So let's move on. First of all, I'll check the chat window. Are there any questions which I have missed out, I won't say it. Let me the questions here. So model contains sheet metal features. The corresponding shell mesh will be formed automatically on the outside face, mid place, or the inside face of the sheet metal. Thickness of the shell features must may not be applied manually. So what is the answer? It says mid plane, which is correct. And what is the thickness of the shell feature? Okay, uh, there are coming and they are mixed. I would include it is by default the mid plane that will be used for sheet metal. It will automatically by the software. And secondly, we need not specify the thickness. The thickness is taken from the sheet metal part. Not. Let me mention, when creating shell mesh manually, ideally it should be defined on the dash plane dash results in acceptable difference of sufficiently large shell elements are not suitable for such structure. Okay. What answer for second question? This is a question for discussion. Um, ID, it does not matter whether we select inside face, outside space, and it is not possible to select. If needs to be selected, then we need to recreate uh, surface. So that is not an option here. We are not creating any surface here. So we'll do that thing. So once it's inside or outside, definitely you have the flexibility. You can select anything, and that is confirmed by the second part of the question, wherein it is asking if I select inside and if I select outside, what would be the kind of result difference? There might be some difference, but it would be very small. As I said, it could be in terms of 0.0001%. And other way around, these are geometries which are eligible for shell elements. In case if you are seeing a big difference, select the internal face and the out face and the inside face, that that time for change. Our geometry is not eligible for elements. Shells can be used to mesh components. So I believe this band to the thickness ratio. So friends, what is the ratio? Thick, what is the ratio? Thin. So this is 10 for solid. Any answer? So any one of the slides we already covered this topic. Okay, let's go to this question. The first is a flat plate with a thickness T is 5 millimeters and our dimensions of 200 by 75. This will also tell you what is span, how do we measure it. So when dashed lines indicate simply separate hinged and the edges respectively. The element type fit for this structure is solid, thick or thin. So thick 5 meters, will it 75 or 200 is the question. And what would be element that we can use here? try to tell what is the ratio. Is it 75 by 5 or 100 by 5, and what is the value? I'm getting some is 100 by 5, which is 40. Um, so one of them is 200 by 5. The answer is 40, which is comparatively making it a thin and thin fine over here. So definitely I'm thinking that direction, no doubt. But that argument actually, here luckily it is ending and we are seeing it just 2 by 5. But it could also be, why not 75 by 5 and look like a comparatively thicker geometry. So it's 20 over there and it can lead to thick also. So just out of experience, I would prefer a thick shell of this particular geometry. To accurately model the stress and strain gradients when using solid mesh, minimum of dash draft quality or dash high quality solid element should be wired in the two. I think this question was done already. Leave it. If sufficient number of elements is generated, solid consider thick shells, consider thin shells, and it will always provide the most accurate solution. We sacrifice a little accuracy by using elements to main features because can we what? Why? We sacrifice a little accuracy by using shell elements to mesh thin features. What are we using? Not absolute silence. I can answer it. Um, Typically, we discuss shear stresses or thin shells will be neglected, and those might be relevant, and we are neglecting them. That is what we need to understand. That's it. Okay, that's it. Check if I have more here. Okay. Let's start from tomorrow. So hopefully tomorrow will be the last day, and I'll finish the rest of the things. Uh, any question to ask?